Chapter 48, Splanchnic circulation. So coming to portal circulation, this includes two capillary beds in series. In this case, the blood flow from the gut, the first capillary blood, flows through the portal vein into the liver, the second capillary bed. Okay. So the blood vessels of the GI tract are a part of a more extensive system called the splanchnic circulation. This is shown in this figure. Okay. So it includes the blood flow through the gut plus blood flows through the spleen, pancreas and liver. The design of the system is such that all the blood that courses through the gut, spleen and pancreas then flows immediately into the liver by way of the portal vein. In the liver, the blood passes through millions of minute liver sinusoids and finally leaves the liver by way of the hepatic veins that empty into the vena cava of the general circulation. This flow of blood through the liver before it empties into the vena cava is called, it allows the reticuloendothelial cells that line the liver sinusoids to remove bacteria and other particulate matter that might enter the blood from the GI tract, thus preventing direct transport of potentially harmful agents into the remainder of the body. The non-fat, water-soluble nutrients absorbed from the gut are transported in the portal venous blood to the same liver sinusoids. Here, both the reticuloendothelial cells and the principal parenchymal cells of the liver, the hepatic cells, absorb and store temporarily from 1/2 to 3/4 of the nutrients. Also, much chemical intermediary processing of these nutrients occurs in the liver cells. Almost all of the fats absorbed from the intestinal tract are not carried in the portal blood, but instead are absorbed into the intestinal lymphatics, that is the lacteals in each villus, and then conducted into the systemic circulating blood by way of the thoracic duct bypassing the liver. Coming to the anatomy of the gastrointestinal blood supply, the superior mesenteric and inferior mesenteric arteries supply the walls of the small and large intestines by way of an arching arterial system. And also the branches of the celiac artery, they supply the stomach, which is not shown in this figure. Okay. So here you have the superior mesenteric artery. Okay. And like that you also have the inferior mesenteric artery, which is not shown again. Okay. So on entering the wall of the gut, the arteries branch and then send smaller arteries circling in both directions around the gut, with tips of these arteries meeting on the sides of the gut wall opposite the mesenteric attachment. From these circling arteries, still smaller arteries penetrate into the intestinal wall. Okay. And spread along the muscle bundles into the intestinal villi and also into submucosal vessels beneath the epithelium to serve the secretory and absorptive functions of the gut. Okay, so here you can see the typical organization of blood flow through an intestinal villus. You can see the arterioles and the venules. Okay, central lacteal. Okay, so there is a small arteriole and venule that interconnect with the system of multiple looping capillaries. The walls of the arterioles are highly muscular and highly active in controlling villus blood flow. Coming to the effect of gut activity and metabolic factors on GIT blood flow. Under normal conditions, the blood flow in each area of the GI tract as well as in each layer of the gut wall is directly related to the level of local activity. For instance, during active absorption of nutrients, blood flow in the villi and adjacent regions of the submucosa increases as much as 8-fold. Likewise, blood flow in the muscle layers of the intestinal wall increases with increased motor activity in the gut. For instance, after a meal, the motor activity, secretory activity and absorptive activity all increase. Likewise, the blood flow increases greatly but then decreases back to the resting level over another 4 hours. Coming to the possible causes of the increased blood flow during GI tract activity. First, several vasodilator substances are released from the mucosa of the intestinal tract during the digestive process. Most of these are peptide hormones, including cholecystokinin, vasoactive intestinal peptide, gastrin, and secretin. These are the same hormones that control specific motor and secretory activities of the gut. They also cause vasodilation. Second, some of the gastrointestinal glands also release into the gut wall two kinins, calidin and bradykinin, at the same time that they secrete other substances into the lumen. These kinins are powerful vasodilators that are believed to cause much of the increased mucosal vasodilation that occurs along with secretion. Third, decreased oxygen concentration in the gut wall can increase intestinal blood flow at least 50 to 100%. Therefore, the increased mucosal and gut wall metabolic rate during gut activity probably lowers the oxygen concentration enough to cause much of the vasodilation. The decrease in oxygen can also lead to a 4-fold increase in adenosine, a well-known vasodilator that could be responsible for much of the increased flow. Thus, the increased blood flow during increased GI tract activity is probably a combination of many of the aforementioned factors plus yet others still undiscovered. Coming to countercurrent blood flow in the villi, the arterial blood flow into the villus and the venous blood flow out from the villus are in directions opposite to each other, and the vessels, they lie in close apposition to each other. Because of this vascular arrangement, much of the blood oxygen diffuses out of the arterioles directly into the adjacent venules without being carried to the tips of the villi. As much as 80% of the oxygen may take this short circuit route and is therefore not available for local metabolic functions of the villi. Okay. Under normal conditions, this shunting of oxygen from the arterioles to the venules is not harmful to the villi, but in diseased conditions in which blood flow to the gut becomes greatly curtailed, such as in circulatory shock, the oxygen deficit in the tips of the villi can become so great that the villus tip or even the whole villus undergoes ischemic death and disintegrates. For this reason and other reasons, villi become seriously blunted in many GI tract diseases, leading to greatly diminished intestinal absorptive capacity. Coming to nervous control of GIT blood flow, stimulation of the parasympathetic nerves going to the stomach and lower colon increases local blood flow at the same time that it increases glandular secretion. This increased flow probably results secondarily from the increased glandular activity, not as a direct effect of the nervous stimulation. Sympathetic stimulation, by contrast, has a direct effect on essentially all the GI tract to cause intense vasoconstriction of the arterioles with greatly decreased blood flow. After a few minutes of this vasoconstriction, the flow often returns to near normal by means of a mechanism called autoregulatory escape. That is, local metabolic vasodilator mechanisms that are elicited by ischemia override the sympathetic vasoconstriction, returning toward normal the necessary nutrient blood flow to the gastrointestinal glands and muscles. So now let us summarize the salient features of the splanchnic circulation. It is also called the hepatomesenteric circulation. The liver receives a dual blood supply, 1/4 from the hepatic artery and 3/4 from portal vein. It receives about 25% of the cardiac output. The splanchnic circulation is characterized by a portal circulation, that is, it includes 2 capillary beds in series. Nervous control of intestinal blood flow. Parasympathetics, they act as vasodilators, and sympathetics act as vasoconstrictors. Okay, there's also the phenomenon of autoregulatory escape after sympathetic vasoconstriction. And also increased intestinal blood flow can be seen with increased GI motility, secretion of peptide hormones, and also decreased oxygen concentration in the gut wall. Also, you can talk about the countercurrent mechanism in the villi. Okay, and the escape thing. Okay. Finally, coming to the importance of nervous depression of GI blood flow when other parts of the body need extra blood flow. A major value of sympathetic vasoconstriction in the gut is that it allows shutoff of the gastrointestinal and other splanchnic blood flow for short periods during heavy exercise, when the skeletal muscle and the heart need increased flow. Also in circulatory shock, when all the body's vital tissues are in danger of cellular death for lack of blood flow, especially the brain and the heart, sympathetic stimulation can decrease splanchnic blood flow to very little for many hours. Sympathetic stimulation also causes strong vasoconstriction of the large volume intestinal and mesenteric veins. This vasoconstriction decreases the volume of these veins, thereby displacing large amounts of blood into other parts of the circulation. In hemorrhagic shock or in other states of low blood volume, this mechanism can provide as much as 200 to 400 ml of extra blood to sustain the general circulation.